एक दिन ओछ्यानबाट उठेर चाहिँ ल आज चाहिँ म एस्ट्रोफिजिक्स बन्छु भनेर that was never a case, right? It's all gradual, right?
Welcome to Science Ka Kura podcast. Today our guest is Dr. Sumit Dahal, who has been my friend since high school. In this podcast, we talk about his research project in building telescope to listen to signal from deep space during his PhD and his current work at NASA. We also discuss the Big Bang, private and commercial satellites, space tourism, and many more. So, welcome, Sumit.
Thank you.
Before we start about your research project, can you give us like small background about your, education a little bit?
Sure. नेपालमा हुँदाखेरि चाहिँ मैले एसएलसीसम्म चाहिँ ललितपुरको आदर्श विद्या मन्दिर एभिएममा पढेँ. अनि त्यहाँबाट ए लेभल गर्नको लागि चाहिँ 2 वर्षको लागि बुढानीकण्ठमा गएँ. अनि त्यसपछि आई टुक अ ग्याप इयर वेयर कलेजहरू एप्लाई गर्नको लागि भनेर छुट्टै टाइम लिएको थियो. वी अल्सो टुक दिस opportunity to like just explore Nepal itself before leaving Nepal. And from there, I went to Abu Dhabi, actually, to in New York University, Abu Dhabi. That was like a pretty new thing at that time to go to the very new university. That's where I did my undergrad. And after 4 years, I started my PhD at Johns Hopkins University. It's in Maryland, United States. I just finished my PhD after 5 years in August. And then I just recently, since September, started my postdoc at NASA. I'm working in one of the specific center of NASA called Goddard Space Flight Center, and that's where I'm right now. So from Kathmandu to NASA in about 9 years.
Awesome. Very interesting journey. So definitely, I think there are lots of things, especially the stories. We're just talking about your place and position now, but could you give us little information about your project as well? Like how did you end up at NASA?
For sure. मलाई पहिलेदेखि नै चाहिँ यो अलि फन्डामेन्टल क्वेसन्सहरुमा चाहिँ बढी इन्ट्रेस्टेड थिएँ म, हैन. I mean, of course, like I was very interested in like developing something like an engineering project. Like you can, के आफूले बनाए सामान हैन, मसिन बनायो अनि ठ्याक्क आफ्नो आँखा अगाडि लाइक यो चाहिँ मैले बनाएको है भन्दाखेरि चाहिँ अलि like you will feel proud. That part was definitely there, but I was also very interested in trying to like answer a little more fundamental question. And undergrad-मा हुँदाखेरि चाहिँ I got this opportunity to go to Italy and do one of this like very fundamental research where we are thinking about like, what is universe made out of? Like, we talk about galaxies, we talk about stars, but there's a lot of things beyond that, which is like, we don't know a lot about. And that like just grabbed my attention in trying to get both of my interests together. Like you can do electronics, you can like try to make electronics, do your analysis and whatnot. But at the same time, you can also think about like all about these fundamental questions, like how did we come here? Like, are we alone in this universe? How, like, what does our existence mean and whatnot? Not from like philosophical perspective, but from like more of a like scientific perspective where you can measure something. So that basically is what like, what got me interested. And, a graduate school apply गर्दाखेरि I was just like looking for like universities that provides things like this. Johns Hopkins University has like a big collaboration with like institutions around, and one of them was NASA. So collaboration, so my PhD गर्दाखेरि I worked on a collaboration. The collaboration is called CLASS in short. It stands for Cosmology Large Angular Scale Surveyor. I mean, we don't have to go into the full form, but it's basically an array of telescopes that Johns Hopkins is leading to make, and NASA is a partner to it. So त्यसरी I think my collaboration started, and when I graduated, they are like, you have some good experience working in this field. Why don't you come join us? And luckily they had a fellowship. So then I joined joined the group there. So in a way, it's a huge collaboration. It doesn't matter whether you're in NASA, whether you're in Hopkins, or whether you are working with some other universities, but it's just like this one goal that everybody has been working on. It's that's what I've been following.
Ani, can you share what was your PhD project specifically about?
Sure. मेरो PhD project specifically चाहिँ के थियो भन्दाखेरि चाहिँ designing these 4 telescopes called CLASS, and the main goal behind developing these telescopes was to study the early universe. Like popular media, people call it like the Big Bang theory. So this Big Bang theory is actually, it does not explain what Big Bang is. It is a theory that basically tells you how universe evolved, but it doesn't tell you what actually happened, like at the very beginning. So what I'm trying to do with these telescopes is I'm trying to understand what that bang is in Big Bang, basically. Giving something physical, giving some physical meaning, giving a mathematical understanding of what happened at the early universe. And we do this by looking at the relic of Big Bang. We call it like cosmic microwave background, CMB bhaन्छौँ हैन? But it's basically this radiation, a background radiation that is everywhere around us. So we have to cut through the noise to get to look into this radiation, which is everywhere. So the telescope that I was working on does not point at a specific star, does not point at a specific galaxy, but it basically looks everywhere in trying to understand this radiation. And by looking at this background radiation, we can tell something more about what happened at the very beginning of the universe. So my PhD project was basically working on this specific telescope. And even, it is a huge telescope, so there's like a lot of people working on it. My specific part was to actually design the sensors or the camera for this telescope. And at the end of my PhD, I worked on 3 out of 4 telescopes. The 4th one is people are still working on it now. But we worked on this telescope, got everything built and assembled and tested here in Johns Hopkins. And then we actually shipped it in a boat after disassembling to Atacama Desert in Chile. And our telescope is actually in a mountain in the Atacama Desert right now, just even as we are talking right now, surveying the sky. So that was what in a summary.
Nice. Okay, cool. So I have a specific question related to Big Bang, you know. So Big Bang, bro, I think it's tens of billions of years ago, you know. So त्यति बेला भएको इभेन्टको एक्जिस्टेन्स अथवा त्यसको केही एभिडेन्सहरू निकाल्ने भने द्याट्स अ भेरी च्यालेन्जिङ टास्क जस्तो लाग्छ. इभन त्यो नर्मल्ली सोच्दाखेरि पनि कसरी गर्छ यस्तो जस्तो लाग्छ नि त होइन. इभन हामी एज अ पिएचडी स्टुडेन्ट बायोलोजी होइन. सो त्यो कसरी हुन्छ त अब समथिङ द्याट ह्यापन लाइक 10 billion years ago होइन. द फर्स्ट थिङ अफ दि ओरिजिन अफ द युनिभर्स भनौँ होइन. सो त्यो चाहिँ टेलिस्कोपको थ्रु हामीले कसरी एभिडेन्सहरू खोज्छौँ?
Sure. So just to give a background on like one of the very good example and how the field started on its own. Your field scene, I think I would say, started by a discovery of through a guy called Edwin Hubble. Hubble telescope is named after him because of what he did. Hubble when he was pointing his telescope around and like looking at like objects, and he just like made a note of like how far an object is. Like object one is like he was looking at galaxies. Your galaxy kati tada cha ra yo kati he recorded its velocity. And interestingly, what he found out was the further out any galaxy is, the faster it is moving away from it. That was one of the profound discovery he made. And this basically ties back to the question of like, how can we even begin thinking about what we see and tie it to the origin of universe? And what this profound result meant is no, and it was not specific to a direction. Your direction, the heresy galaxy farther out move हुने थिएन क्या. जुनै direction मा हेरे पनि हैन, everything was moving away from you. And you can't say that we are special. Like, we are not, unfortunately, we are not special. So anywhere you are on the universe, you look around, things are just moving away from you. And the farther you are looking out, the farther out they are moving. So the only conclusion you can draw from this thing is universe is expanding. Because imagine you are like thinking about a balloon. You're like staying on like one part of the balloon, and balloon puktahari, like you're like standing on somewhere. Like no matter which direction you are looking at, things are always going to be expanding away on and on from you. So that is the future. Which means like if you were to draw this conclusion, same thing and go back, what's going to happen is like universe had to start from a singularity, right? It had to start from something. Can expand if you were to go back, it has to start from somewhere. So this is where it all started from, and people said, okay, so this is what we call a Big Bang theory, where the universe is basically expanding from a singularity and going on and on. And of course this was how it started. But there has been like lots and lots of other observational evidence suggesting that this is what is happening. So a question of like, it's a very good question also, how do you even like, think about like studying these things now? So being in Earth itself, you have to deal with a lot of noise, because there is a noise from your atmosphere. There is a noise from like, whatever is going on around you. And another thing is like, you're trying to study what happened at the origin of the universe, but we live inside a galaxy, our Milky Way galaxy. So you have to, take that signal out from that galaxy as well to get to what you're like trying to look for. So you need to develop a telescope, which is one, very sensitive, so that you can actually like look into, this like, small signal that you're trying to look for. And the second is you need to develop something that can actually separate your signal from your noise. Sensitive if it is looking at your noise and your signal at the same way, there is no way you're going to identify, oh, this is my signal and oh, this is my noise. So we had to come up with something like you have to innovate a technology where you can look at your signal but not focus on the noise. I actually have a very nice, this is what I was talking before the show. I have a very nice demonstration of how we actually do this. And it might be familiar for like a lot of engineers. This technique is called like a modulation, but let me share a like little sound bite, which basically demonstrates how we can actually find this small signal, or like trying to find a needle in the haystack, basically. Let me share my sound. Okay, I'm going to share the sound. Share. Okay. All right. So let's just say that, the signal that we are looking for from our early universe is something like this.
The cosmic microwave background polarization.
Oh, you guys heard that? Okay. So let's say this is the signal that we are looking for. Somebody just said the cosmic microwave background polarization. It was my professor actually, but of course this is a signal you are looking for, and that is not what you get at when you are making a telescope. So what happens is there's going to be a lot of noise, something like this. So now, when you are like building a telescope, what you actually hear is a combination of both of this, something like this. So of course, the question is like, how on earth am I even going to get to that signal when there's so much noise around you? So what you do is you modulate the signal that you are looking for. What modulation means is you are basically shifting the frequency, or I mean like pitch. So you shift the frequency of your actual signal to be something like this.
The cosmic microwave background polarization.
Your signal, I just like change the frequency of that signal. I did not change the frequency of the noise itself. Now what happens is, now what your telescope is going to record is something like this.
The cosmic microwave background polarization.
So this is just like a very small demonstration that I was trying to explain to a general audience how we actually get to measuring a small signal when you have tons of noise. And so, just a small technique of how we go about, discovering this small signal that is everywhere, but that is like submerged within noise. And that is the work that you have to put in, basically.
All right, awesome. So while we're talking about signal here, so what exactly is the signal? Like, is that some form of wave? Do you hear sound as well, or is that an image? के चाहिँ होला त्यसै?
So this signal is basically a radiation that is everywhere around us. You just need, it's just a background level noise for noise in a way. And it comes in microwave radiation. किन चाहिँ micro भन्दा हामीले भात पकाउने microwave जस्तै हो. There is no difference. Because even that microwave basically uses microwave radiation to cook your food. Our universe started universe started in a very hot state, hot and dense state. So it would be emitting like higher radiation, highly energetic radiation, something like gamma rays or even farther than that. The universe expand हुँदै गइसकेपछि चाहिँ हैन, your energetic waves basically get stretched out, rubber band तन्के जस्तै. And when you are stretching out these highly energetic radiations, what happens is it cools down to radiation that is less energetic. 14 billion years ago, the universe started. If it was emitting like some highly energetic radiation, it has today cooled down to microwave. So when you are looking around, you have to basically make a microwave antenna that basically reads background level of microwave everywhere. Opposite of what we know as microwave. हाम्रो भात पकाउने microwave मा चाहिँ भात पकाउनु like just like heating something, like heating your food up. These things are transmitters, so it will basically generate microwave radiation. You need to make a telescope that is opposite, something that will receive these microwave radiation. Of course, the intensity that we're talking about is very small. Interestingly enough, actually, this is a signal that we are all familiar with, but we did not know this before, which I didn't know when I was a child. हामी पहिला सानोमा बच्चा हुँदाखेरि टिभीमा त्यो टिभीको त्यो फ्रिक्वेन्सी ट्युन गर्दाखेरि चाहिँ झ्यार आउँथ्यो टिभीमा त्यो अनि त्यसपछि हामी चाहिँ कस्तो झ्यार आयो टिभीमा अलिकति एन्टेना त्यो यताउति हल्ला त भनेर हामी एन्टेना मिलाउन जान्थ्यौं नि. That is basically what it is. That snow that we call like snow, that snow you're tuning into when you are going from one frequency to the other frequency is a type of it is a type of an antenna. It is an antenna that is like recording about 1%. Now, of course, as I was talking about earlier, there's a lot of noise you have to deal with, but 1% of that signal, the Jarrauni signal, is coming from Big Bang, is coming from the early universe. So even something like that would help you understand. But of course, if you want to go more into trying to actually study more about this, you have to build a sensitive instrument. But it's something that we have all been familiar with for long time, but just at least I did not think about that.
Talking about antenna, it's like most of the biggest telescope are in most isolated place. Why is it important for them to be in such remote and where there's no sign of any human beings?
A couple reasons. I mean, the first reason is if you are, for example, building an optical telescope meaning something that human eyes can see. If the telescope you want to make sure you are away from light pollution. I mean, as simple as it is. If you're trying to look into something out there, you're just ruining your eyes, right? Because you're not going to see something farther out. So you need to be away from light pollution. You need a darker sky. That is one thing. But in terms of the telescope that I built, because I'm building microwave telescopes, so you basically want to be away from as much noise as possible. And turns out, for the specific microwave frequencies that I'm working on, the two biggest sources of noise, or the two basic microwave emitters, are water and oxygen. एटमोस्फियरमा हाम्रो वायुमण्डलमा भएको oxygen र water vapor चाहिँ they also emit a microwave in the exact same frequency that I'm working on. So what you need to do is you need to go to a place that has the least amount of water and the least amount of oxygen in the air. So to get the least amount of water vapor, you need to go to the driest spot on Earth. And the driest spot on Earth is Atacama Desert. That's why we go to the Atacama Desert to put our telescope, because it's very dry. Some people also actually put telescopes in the South Pole because it's actually like the driest spot. I mean, it's a cold desert, but it's very dry. And recently, people have actually even considered Tibet as a potential site to put these kind of telescopes. The other thing is oxygen. So to get as least oxygen as you can, you need to go higher up as much as possible. So it turns out that the Andes Mountains in the Atacama Desert are like perfect location for this, because you are about like 5,000 meters high, and in the same time, it's also very dry. So these are the reasons why people are like going for like remote locations. I mean, even better, if you can afford money, if you have just $1 billion lying around you, you can make a satellite for yourself and just like launch it into space. So you got no water, you got no oxygen. So that's you basically build what your money can buy you. But to be honest, like what we are trying to prove with our telescope is like, you can do it with less money as well. Like, you do not have to go to space to do this. Sure, like, it will be amazing, and, there's a lot less noise you have to deal with, but what we are trying to show with our telescope is you don't have to go to space. You can go to Atacama Desert and do it, which is much easier, just, a day's flight from North America here.
And you said like तिमीले चाहिँ like 4वटा telescope build गरेका थिएन अनि
Sure.
are these telescope like independent of each other, and or like how do they communicate with each other, I would say?
So they are indeed independent. They independently take data, and all the, like, let's say, combining of the data happens like in a post observation. We do through like writing programs and whatnot. The reason we have 4 different telescopes is what I mentioned like the noise sources like water and oxygen coming from Earth itself. But no matter what you do, even if you build a space satellite, what happens is you have to deal with Milky Way. Because trying to look at the signal that is coming outside of the Milky Way, that's where, all the signal of the origins of the universe is coming from. But you have to deal with the Milky Way. And it turns out in the Milky Way galaxy itself, the 2 biggest source of noise are, this gets a little technical, but basically we are building these 4 telescopes at slightly different frequencies so that, for example, what we call in our field is just dust, are basically carbon molecules that are just spinning around or being like accelerated by some sort of like magnetic fields. These sort of things also emit microwaves. So if you were to build your telescopes that is sensitive to slightly different frequencies, what you can do is you can like then make a model so that you can actually get rid of the noise that is coming from the Milky Way. To explain shortly. For example, I was talking about dust. So let's say one of the telescopes is slightly more sensitive to dust than the other telescopes is. Then at the end, what you can do is, मेरो एउटा telescope चाहिँ dustसँग धेरै sensitive, so it has this much signal. The other telescope, which is not as much sensitive to dust, has this much signal. So you can do some sort of like signal subtraction to basically try to minimize the noise as much as possible. In a way, to summarize, building 4 telescope is our way to minimize the noise coming from the Milky Way so that we can hear the signal coming from like farther beyond.
Project like this must have a lot of challenges, like lots of challenges. Can you share some of the methodological like challenges while building telescope, or while traveling to go to the Atacama Desert as well?
For sure, yeah. I mean, the first is definitely a technological challenge, because if you were to tell somebody that we are going to do this 50 years back, they would be like, you guys are crazy. You're not going to be able to do this. because the signal that you're looking for is like submerged in so much noise that you're like, this is not going to happen. Or they would tell you that you need to go to space. There is no way you can do it from Earth. But 50 years down the line, we are developing technology to a level where we're like, look, we have developed this technology. Now we want to like use this to study something that people have not done before. So the problem starts with like, पहिला बेला क्लासहरू पढ्दाखेरि यसो कसैले प्रोफेसरले क्वेसन सोध्यो भने चाहिँ यसो आएन भने चाहिँ गुगल गरेर एन्सर पत्ता लगाउँला नि त भन्ने हुन्थ्यो होइन अब अहिले nobody has done this before. Like you are trying to do this like for the first time. Of course, there is experience from people who have worked on this field forever. So these are the experts who you can rely on to give you good suggestions. But other than that, you're on your own. So because of that, like there are like lots of challenges that you don't even expect. One of the technologies that we're using to make our camera, like camera telescope, the sensitivity of this camera comes from using superconductors. To explain superconductors, basically, हाम्रो कम्प्युटर्सहरूमा हेर्दाखेरि चाहिँ हाम्रो कम्प्युटर्सहरू जुन चिपहरूले बनाएको हुन्छ we call them semiconductors as opposed to like हाम्रो घरमा भएको वायरिङहरू चाहिँ it's just like a normal conductor. Superconductorको एउटा specific nice feature चाहिँ के छ त भन्दाखेरि below a certain temperature, we call it critical temperature, त्यो temperature भन्दा तल operate गर्यो भने चाहिँ it just has like zero resistance when you're operating that superconductors. So that reduces a lot of noise. That is how we become sensitive. Because at the sensitivity that we are talking about, electrons go movement it's noisy. So you gotta get rid of that. And to get rid of those noise that is made by basically electrons vibrating in your conductors or even your semiconductors, chips, what you do is use superconductors. But the problem with superconductors, these days at least, is you have to go at ultra low temperatures. So the temperature that I'm talking about is like near absolute zero Kelvin. So we operate at millikelvins. We are talking about like 100 millikelvins. This is, just for general audience, this is like what? 273 degrees below zero. It's crazy. And like at that point, you are like basically at the lowest theoretical minimum possible. So you have to develop technology that can basically get your camera all the way down to that temperature. So it's not just developing camera itself. The challenge comes from that you have to keep it at that ultra low temperatures. So that is like that has been one of the biggest challenges for us. There has been technologies coming up that helps you operate your sensors, your camera at these cryogenic temperatures, but it brings its own challenges. That is one. The other thing is just understanding how like the theory on its own is challenging on its own, right? Because before you even proceed to like think about, oh, this is what I'm going to look at, you first need to understand what you're actually looking at and what is the exact signature that you're trying to discover. I know. You just point your antenna anywhere and then measure the signal. That's not going to get you anywhere because you need to be specific about, okay, I'm looking for this exact specific signature and I have reduced enough noise that I can tell you that, oh, this is my signal and this is just not noise. So for that, you need like lots and lots of, observations and theories that people have worked for like centuries now. So, of course, there is a technological aspect, one that I was talking about before. But the second one is this like theoretical aspect where you need to be standing on a strong theoretical basis before like moving forward. And I guess the third aspect would be like logistical challenges, So the telescope we are working on is 5,000 meters high. What that means is you are working on 50% less oxygen than sea level. So I have had times where like the first day you drive up the mountain and you are getting dizzy after like an hour because one, you are already breathing less oxygen, like 50% less oxygen. And second, you are trying to build a freaking telescope, which is like huge. So And you have to do math up there in the altitude. So we'll just we're Skyping or just using Zoom and whatnot with folks down here in North America, and then we're like, okay, just do this addition, do this subtraction, do whatever you need to do. Just tell me what I need to do. I cannot do any math up there. So it's working at altitude brings its own challenges. We used to joke around and we call it mountain madness. Somebody breaks something and it's this guy has been hit with mountain madness today. It's
So with your class project during PhD,
Mm-hmm.
what were the major findings?
I would say that rather than saying that there were any major finding, the thing with bigger projects like this, it takes years and years to make. So it started it even started paperwork way before I even joined the collaboration. And to get to a level where you can actually say, okay, these were my science goals and these are my findings and this is what I can tell. It definitely takes on a time scale of somewhat a decade. So we definitely, during my PhD, we definitely worked on getting all these instruments out and making sure everything works. And on a smaller scale, there were a lot of technological check marks that we made where we are look, this is for example, the modulation technique that we talked about. Up until when I started, that technology wasn't even demonstrated well. People thought, oh, you can't do this. It's not going to work because of XYZ things. But demonstrating that, no, look, I made this thing and it works out in the field. And through couple years of data, you can say that, okay, look, I'm now able to extract the signal that I'm looking for and suppress the noise. So those have been demonstrated in the field. And now we're basically trying to get to our science goal, which is going to take some time, but we are getting there. We have demonstrated things worked properly, and it's just you have to take more data, analyze more data, and to go back, actually, we actually don't know. We actually don't know what we're going to discover because this is something we have expectations. So people have told us before that, the level of signal that you are looking for should be below something or let's say above something. They have set us a benchmark because if our signal, for example, were to be stronger than the benchmark that people have put before, then our universe would not have existed the way it is today. Then there will be questions. Okay, there's something wrong with the theory. But below that benchmark, it could be anything. Or to even throw it out, it could be that inflation, this theory is called inflation, basically trying to figure out what happened at the very beginning of the universe. Maybe the theory is it's not true. It would be even more interesting if it was not true, because then we have to come up with a whole new theory and try to explain the things we see around. So one question is what level of signal are you expecting? And the other is is that even true? We don't know. We have to wait. We have to put some work in, and and we'll see.
And how long do you think will you guys will have to collect the data to get a concrete? I mean, because you guys cannot predict, right?
For sure.
Signal filter out something. I think LIGO, when they were testing out LIGO, they had built the machine, but example pound time lapse that once they figured out one example and they subsequently could catch more of those signals.
Sure. So just looking at the sensitivity that we have, and just given that your telescope is this much sensitive, and if we were to believe on the most popular theories these days, everybody has anybody can come with some crazy theories, but let's say if we were to believe on the most popular theory, then we would say at the sensitivity of our telescope, within the next 5 years or so, we should have some sort of concrete scientific finding. But the scientific finding could also be that at this sensitivity level, we did not see anything. That is also a very good scientific argument to say that, look, all these theories that you came up telling how universe evolved from, being a hot and dense singularity to this day doesn't seem to work that well. So it looks like we need to, come up with something different. But let's say if whatever we believe so far, the most popular theories, then I want to say like 5 years is probably, a rough margin.
That's very optimistic.
Exactly. Yeah, that is being optimistic for sure.
Like talking about optimism, what would be your once you prove certain theory that you guys wanted to prove, what would be its kind of significance, kind of way?
Okay. I think the first thing is, as I was talking about before, is like more fundamental in nature. Even if we were to prove that this is how the universe evolved, it is not going to change anybody's day-to-day life. But I am studying this because it's in a more fundamental level. We are humans, right? This is what wakes me up every morning, trying to understand the more fundamental thing than just like a day-to-day life. It will give us more insight into like other things. For example, not only are we going to study about what happened in the origins of the universe, but our telescope can also shed some light on what happened in the cosmic dawn. Cosmic dawn is basically when the first stars were born. When the first stars were born, these stars emit ultraviolet radiations. This ultraviolet radiation basically changes the entire dynamics of our universe because it is so energetic that it ionizes like hydrogen and whatnot gas around. So it just changes the way universe evolved. So knowing when the first stars were born is basically, our sun is a star. It basically helps you understand how we came here till today. It just shapes our understanding even more than what we had thought. Another example of is if we understand the origins of universe better, that is the best lab we can ever create to understand what we call quantum gravity. It might be throwing big words here, but it is basically these kind of experiments. We cannot do it on any tabletop experiments. You can spend billions of dollars in trying to understand how quantum gravity is basically a field where two of the biggest fields of physics that we all know of, quantum mechanics and general relativity. This is where these two big subfields of physics come together. So understanding this, like what happened in the Big Bang, is like, you are getting this amazing lab where you can study things that are so energetic and that happened like 14 billion years back, which you can never do on any university level experiments on a tabletop or colliders and whatnot. So those are like, I would say like more towards like, getting look at like what happened, like, when civilization started. People were still curious back in the days about what they saw in the night sky. And still today we are curious what is happening. So we are just like, passing our knowledge from one generation to another generation. And we are just like churning out this like wealth of knowledge that we know as like humanity on its own. Orkukurachi, I think, of course, there's always going to be questions about, so is there any practical implications of what you guys are doing? And totally, there are a lot of things that can come out of experiments like this. So, whenever there is like some sort of technological advancement, I think it is fair to say that a lot of these technologies were developed when there was a drive for it, like when there was a reason to develop something. One of the examples that I can give is cameras have developed so much these days that everybody can just like whip out a phone and take like amazing pictures these days. But to get to that level, NASA and Hubble Space Telescope had to spend years and years trying to make this CCD's camera better so they can look farther out in the universe and take amazing pictures of the galaxy. So there was this drive. You never know what happens with the technology that you develop today. Similar thing that I'm talking about now is like with this advancement of superconductors. We're spending so much money and so much energy into developing this sensitive superconducting cameras that 10 years down the line, who knows what you can use that for. But if we do not invest time and money now to develop these kind of amazing technologies, 10 years down the line, we'll have like no new innovation, right?
भर्खरै तिमीले मेन्सन गरेको थियो होइन के अरे हाम्रो क्लासिकल फिजिक्स भनौँ न क्लासिकल भनौँ कि के भनौँ अब मोडर्न फिजिक्स जस्तै लाग्छ त्यो थ्योरी अफ रिलेटिभिटी पनि होइन हाम्रो लागि चाहिँ अब that fails at some level in when you are trying to explain gravity in subatomic level or quantum level भनेर जस लेखेको थियो तिमीले एउटा साइट पठाएको थियो होइन त्यो पढ्दाखेरि so I was just curious how things are different at subatomic level होइन so quantum level मा चाहिँ किन अब theory of relativity ले gravity explain गर्न सक्दैन त्यसको बारेमा अलिकति layman term मा भनेर भन्दैौ न
So I think this is to be honest, you just asked the question that we have been trying to figure out for like almost a century now. A more like general answer to this question is we actually do not know. What we know so far is, so back in Newton's time, he had this classical theory of gravity, where gravity, school ma padhadahari pani we studied gravity as a force, right? So gravity is something that attracts 2-3 bodies having masses. That is how things were explained. Quantum mechanics was not that developed till at that point. And then like later on, we have this general relativity come up, where Einstein said not just Einstein, he definitely put a lot of work on it, but he had, help from a lot of amazing mathematicians and whatnot to come to the level of our understanding of general relativity till today. But what Einstein did is like, he said, okay, because there are things that when you're looking out in the universe, it doesn't, classical gravity, or like when you think of gravity as a force, it doesn't explain everything that you see around in the universe. For our like general, like if you're thinking about like a car's velocity, if you're thinking about like playing ball, if you're thinking about things like this, you don't really need to use general relativity. So classical mechanics, Newtonian mechanics still works. It is still going to give you the right answer. But once you start talking about huge bodies, like massive bodies, like stars and even like, big planets and whatnot, and like evolution of universe, things start breaking down. So, you cannot apply classical mechanics then, because what classical mechanics predicts is going to give you something different. So what Einstein said is, you know what? I'm not going to think about gravity as a force. I'm going to think of gravity as just something, it's like a perturbation in, now this is going to get a little complicated, but it is basically a sort of like a fabric of space-time. He said, you know what? I'm not going to think of gravity as a force. I'm going to think of gravity as a geometry. In a way to explain it is, it's not that when you हामीले बल फाल्दाखेरि बल माथि गएर बल तल आउँदाखेरि चाहिँ त्यो फोर्सले तानेर आएको भन्ने चाहिँ न्यूटोनियन मेकानिक्स भयो तर फोर्सले गर्दाखेरि आएको होइन अर्थले चाहिँ स्पेस टाइम कर्भ बनाएको or like this fabric curve बनाएको र त्यो ball is just simply following that geometry. Anything with mass changes the geometry and you are just following the rules of that geometry. That is it. So basically moving from force to geometry. That is one thing. That is one development that happened in the 19th century. The other development was quantum mechanics. So when you are looking into like small, like minute things, let's talk about like electrons and whatnot. Similar thing happened where like similarly how like classical mechanics broke down when you're talking about huge bodies and then, but general relativity did. Similar thing happened in like small, like minute scale where classical mechanics, when you apply like, example, F equals to ma, if you just apply F equals to ma, it is not going to work and not going to give you the right prediction on when you're working on like electrons and like, you know, things even smaller than that. So somebody had to come up with a different theory and they came up with quantum mechanics. And the problem of our generation right now, so they solved those problems. The problem of our generation is what general relativity predicts in quantum level or like minute level is different than what quantum mechanics explains in certain phenomena. Same thing, the opposite. If you were to apply quantum mechanics and try to get some predictions from, in like when you're dealing with like huge objects, they're not quite compatible. So there is something where these two things don't really give you the exact same answer when you're like trying to go across the regime. So that's why people are trying to come up with this thing called, quantum gravity or something that would explain things in both levels, whether it's small or whether it's big. But what is that theory going to be? We'll have to wait for that. We don't really have an answer for that.
All right. So basically paraphrase गर्नु पर्दा चाहिँ जस theory of general relativity ले normal days मा हुने observation को साथसाथै big bodies हरुलाई पनि explain गर्न सक्छ, तर general relativity ले चाहिँ हाम्रो क्वान्टम लेभलमा अथवा सब एटोमिक लेभलमा हुने बिहेभियरहरु चाहिँ एक्सप्लेन गर्न सक्दैन. सो वी नीड some other theory for that, and okay,
correct,
that makes it more clear.
For sure.
Thank you
and it goes the other way around too, like exactly same thing for quantum mechanics too. So it's like they're amazing theories in their own regime, but once you try to cross the regime, then we start seeing problems.
Oh, okay, cool. So that's where theory of everything comes in.
Correct. Correct. So, theory of everything will be like, it's like I don't know, you can say that it's a fiction, you can say it's a dream, you can name it anything, but that will be one, like in Lord of the Rings, one theory to rule them all, basically.
Alright, cool.
Yeah, that'll take some time because, but there have been a lot of advancement on that, to be honest, because theory of everything, since we're on this topic, universe force or any activity, you can basically boil it down to 4 fundamental forces. Anything you see can be explained with these 4 fundamental forces. One is gravity that we talked about. The other is electromagnetism, we all know of, and we are communicating right now because of all the amazing things that we knew about electromagnetism. And the 2 other forces, because physicists sometimes are not that clever in naming things, are called weak and strong forces. These are the 4 fundamental forces. Strong forces are what binds protons together. Because, if it was just electromagnetism, plus and plus would be repelling each other. But when you look at something, protons are all tightly bound together in a nucleus. So that's a strong force acting there. The other weak force is basically that is what explains radioactivity, for instance, I know. Uranium breakdown, all these things. And these are 4 separate forces, or that's what we thought. And somebody came up and actually they explained a thing called electroweak theory. So electroweak theory basically combines electromagnetism and weak force together. So there is now only 3 things: strong force, gravity, and electroweak theory. Now the question is, can we do more? Can we come up with a theory to combine these 3 forces together again? And if we can, that'll be a theory of everything. So you have this one amazing theory where you don't have to tell, oh, I'm talking about strong force now. Oh, I'm talking about gravity now. You don't have to do that. You can just apply one thing and it will just predict what happens.
Ani अहिले तिमी नासामा पनि यही same project मा involved छौ?
I'm involved in the same project as well. I'm more in a guiding level. I'm not doing the day-to-day work that a lot of other collaborators are doing. But because I've worked on this for so long, I always attend meetings and then we can decide on our next step for our next telescope. But I'm working at NASA, I'm working on the same goal, trying to understand what happened in the early universe. But this time we're trying to do something different. And in this case, what we're doing is we are putting a similar kind of telescopes in balloons, and we're going to launch this telescope up in the balloon. So this is going to be somewhere between ground and space, right? Because sure, if you want to go to space, that'll be amazing. But these are billion-dollar projects. And ground is that's okay, you demonstrate your technologies in ground. And then balloon is kind of somewhere in the middle because, you get higher than like a troposphere. So you're flying your balloon in a stratosphere. So you get rid of a lot of those things that I was talking about. You get rid of the noise from water, most of it, and you get rid of a lot of noise from oxygen because you don't have to, and then you don't have to drive all the way up to the mountain. But of course, there are challenges with like balloons as well because, you have to be very specific in terms of time when you can fly. It is weather dependent. You have to rely on like a lot of other technologies to make sure that the balloon is flying properly. So it brings different challenges, but I'm working on, in terms of the big picture, it's still the same thing, but trying to do a similar thing, but with like a slightly different approach. And one more thing on this is like, the next thing we're trying to do here is like, prove like as a technology demonstration for like space projects. So let's say if you propose a space mission down the road, you want to make sure that this technology holds up properly on like balloons, because the environment that your camera and your telescope experiences on like stratosphere is like very similar to the environment that it's going to be more challenging, but at least more similar than what you would experience on the ground. So it is also a test bed for like a lot of technologies that you see in space. I would say that most of the technologies that we see in satellites was probably at some point, at least the big equipments were tested in some sort of like balloon facilities, as a test bed to make sure that it at least works out there.
Okay, so like talking about like NASA, like SpaceX has kind of moved this pursuit towards our space goals kind of in a good way forward. And what do you think? Like, how do you perceive this collaboration between NASA and like private enterprises like SpaceX? How can they symbiotically move ahead so that like we can do educational as well as industrial stuff?
Sure. I think the level of like innovation we are talking about these days and like looking forward into future, we definitely have to be collaborative. Like all the sectors have to come together to achieve a single goal. Because I would say that, the days where we can just perform an experiment on a tabletop and try to get some science out of it, still some experiments are possible, but most of these requires like huge amount of effort and collaboration from people. And I think different sectors bring like different sort of expertise and different like pros and cons with them. So I think it is definitely true that having industry help out government sectors or even like university is definitely the way to move forward. For example, like one thing I can think about in my field, at least where I come from, is when we develop these kind of like cameras, we are in a regime where there is no way you can make a single pixel better. हाम्रो क्यामेराको per pixel sensitivity को कुरा गर्दाखेरि हैन, the reason is we are hitting this thing called quantum limit. No matter how much research you put onto it, fundamentally, theoretically, you are at the lowest or like highest, lowest noise and highest sensitivity that you can achieve. So it is not because of we can't make it, we don't know how to. You just can't because you hit the theoretical limit. So the only way to make a camera better in our regime is to pack more things together, more pixels together. You're going to keep packing more and more pixels together. So you're going to have to make more of something, mass producing something. Now, this is where we need industry, because I can't be sitting in the lab trying to make something again and again using the technology we have in our lab, because our labs, our government labs, where I'm working at, are not equipped for mass production. So how can you make something better when you need mass production, but you don't have those capabilities? So I think this is an example where an industry can jump in, and we are trying to like collaborate with industries on this aspect. So this is where industry can jump in. One example. But I think on the other hand, there is also, people are also skeptical about this, because one of the main reason is most of the private companies are driven by profits. That is not what most of the universities and government agencies are doing, because they're using taxpayers' money. So the science that comes out of it, the data that comes out of it, should at the end, it is public for public consumption. On the other hand, I don't think that is what drives most of the industries, because most of them are profit oriented. Excuse me. So I think there should be some sort of balance between industrial goals, like goals from private companies, and the goals from government, so that maybe we can find this middle ground where, we can achieve both together. And that would really be amazing. I mean, in the question you asked about SpaceX thing, I mean, they have been doing something amazing. For example, they have been innovating so much because they have not had so much constraints as you are working in a government agency, because we all know bureaucracy. So when you're dealing with so much bureaucracy, and when you remove that out of your equation, there's a lot of innovation, especially in terms of risk factor, because you can, in a private company like SpaceX, I believe, take more risk approach as opposed to, for example, in NASA. So I think there's definitely both ups and downs, but I think there is definitely a way where we can come into a middle ground and move forward. And we do need this collaboration. I don't see one agency, just a government or a private sector, taking it all the way to the finish line, whatever the finish line is. But yeah.
So I'm just planning to ask you a layman question. We think about this satellite, which are orbiting the Earth, होइन? अनि त्यसपछि recently अब SpaceX को अब how it is revolutionizing the space technology and all, satellite are being launched more often, होइन? So just तर कति भइरहेछ के भइरहेछ त हामीलाई केही पनि थाहा छैन एज अ जेनरल पब्लिक भनौँ न. सो एक्चुअली अब स्पेसमा कतिवटा स्याटेलाइटहरू छ त मतलब अर्थलाई चाहिँ रिभल्भ गरिरहेको, होइन? सो इज देयर रियली मोर, होइन? त्यो के छ स्पेसमा?
Yeah, that's a lot. I don't think I can put a number on it, but I would say upwards thousands of them. Because there's a lot of different kinds, I think, but most commonly are communication satellites. For example, we are talking right now because our data is definitely being sent through our nearest cellular network or whatever network these companies are using, communicating through satellites and whatnot. So I think there's a lot of private companies using communication satellites for TV or for communication like this. And there are other scientific things where we are doing science. Both I think actually we are, I would say, in terms of satellites that we work on, telescope pointing outside away from the Earth, I think we are in a small group when you think about a tiny group when you think about what is out there, because most of them I believe are pointed towards Earth and not away from Earth. And of course one is because communication satellites, and the other is monitoring a lot of climate things, because for example, the weather patterns, you open your iPhone, you open your computer, and you can tell what happened. Hopefully you can tell whether it's not going to snow or not tomorrow. And all these weather stations rely heavily on these. And there's whole another industry that I have very little knowledge about, but I know there's a lot of them, are military satellites. These are, of course, it's heavily yeah, I mean, there's a lot of security around it, and I don't even know how many of them are out there, but there are a good amount of military satellites out there, that's for sure.
So I had been hearing about space pollution as well, which was completely a new term to me, to be honest. So is that a possibility now, with lots of explorations going on, and there's a possibility for space tourism as well, so हामी मान्छेले चाहिँ जता पनि गएर जोस् आफ्नो अब एउटा फुटप्रिन्ट छोड्ने अब इन अ नेगेटिभ वे भनौँ न, होइन? सो इज द्याट गोइङ टु बी अ प्रब्लम इन द फ्युचर? व्हाट डु यु थिंक?
For sure. I think there is definitely what we call a space junk. There is definitely a lot of space junk around there. So definitely people have to be mindful about that. There are definitely rules and regulations of like what you can do and what you cannot do. The problem comes when international community do not come together to abide by same rules and regulations, because everybody gotta play this by the same rules. Yeah, so we have to all be mindful about this for sure, and not creating more space junks. I think one is everybody has to play by same rules and regulations. The second thing is also, I think monitoring is definitely more important as well. And I believe I can't remember it on top of my head, but there is a way you can actually monitor almost any, if it's not a spy satellite, of course, monitor like all these like space things that are orbiting around the space. Even it's available publicly. I can't remember it on top of the actual website on top of my head right now. But and there have been instances in the past. There have been instances in the past where telescopes or even satellites have been hit by like random space junk. So it is not that it is a futuristic thing. It has happened already. And just to add like one more layer to this, it is not just that we are affecting the satellites up there. You can actually affect our own observation of the sky. For example, with this there were recent talks about SpaceX Chainlink satellite or something, where they are launching. Is it SpaceX? Yes, it's SpaceX. Where they are launching like a chain of satellites up there, and it's so bright that if our sensitive telescopes like ours were to point towards that part of the sky, you are completely blind, because it is like, so that, of course, like later on they looked into this thing a little bit more, and they said that it is not the final position of the satellites, because these satellites are supposed to be like diverging and like spreading out more, so you're not going to affect the telescopes like looking from Earth. But yeah, these are all definitely concerns, and something definitely to watch out for the future as more and more things are being launched in the space.
I see. So yeah, with the so definitely there is going to be same limit. So अहिले त्यो कार्बन इमिसन भएको जस्तै मतलब हुन्छ नि, हामीले नेट जिरोमा जानुपर्छ भने. सो अहिले डेफिनेटली अब कन्ट्रीहरू जसले चाहिँ स्याटेलाइट लन्च गरिरहेको छ, दे आर द फर्स्ट वर्ल्ड कन्ट्रिज, रिच कन्ट्रिज होइन. सो आर कन्ट्रिज लाइक नेपाल एन्ड स्पेसली लो इन्कम, मिडल इन्कम कन्ट्रिज आर गोइङ टु ह्याभ सम स्पेस on the space satellite launch got it, for example, Nepal. So is that going to be a problem in the future? Has that been considered for countries like Nepal as well later?
Communication satellite, I think like a lot of countries have already done it. Like I'm sure like hundreds of countries have launched their own communication satellites. But in terms of like going beyond the capabilities of communication satellite, can you do some science out of it? For a country like Nepal, I think so far there have been I've been hearing about like mini satellites. These are things called CubeSats, where it's just like a small cube, I think, where you can hitch a ride with a bigger satellite or a bigger rocket, and you can use these like small satellites. And these kind of satellites can be afforded on university level these days. Like, a university can afford these satellites. So these are something definitely like Nepal can make improvements on. But now if you want to like go to like beyond, like mini satellites, and like thinking about like, when will Nepal be able to launch its own satellite and we can be proud of that? I think there is a, big lesson to be learned here. I think there is a lot of lessons we can learn. It's very inspirational, because thinking about like, sure, we have India it's very different in terms of economy as compared to Nepal, but there's a lot of similarities between us. And one of the things that they have achieved is, for example, talking about Mangalyaan. This is a orbiter that they launched, I think 2014 or maybe before that, but Mangalyaan was successfully launched to Mars at a fraction of cost that organizations like NASA or like European Space Agency would usually put on projects like this. So so it is not just about economy, because India has demonstrated that you can do it using things like homegrown technologies, using manpower from your own country, using technologies that you do not have to import from other countries. That reduces the cost by a significant amount. I mean, of course, there's still a long way for Nepal to launch a satellite like Mongolian, for instance. But I think, there is a lot of inspiration coming from just like near us. We don't have to venture further out in terms of thinking about like how we can, get ourselves into the space race. But again, another part and layer to this also is, now people are thinking not just about satellites that revolve Earth, but we're thinking about interplanetary satellites. Like Mongolian is a perfect example, because it does not revolve Earth, it revolves Mars. And you can learn more about Mars from there. So space is so vast and we're just so tiny things that I think there's definitely going to be space for everybody, for sure. We just have to get there.
So we kind of know like your short-term goals, right? You're working currently to launch your telescope using balloons. Does your long-term plan involve you traveling on a rocket to the space and launching, like putting the telescope by yourself in space?
I think that would definitely be like a dream come true from from when I was little. But I think it involves for me, I think like, of course, बच्चा बेला like TV हरू हेऱ्यो अनि ल म चाहिँ यस्तो बन्छु है, म चाहिँ नील आर्मस्ट्रङ बन्छु ठुलो भएर भन्ने यस्तो हुन्थ्यो हैन. But like as you grow up, I think you realize the amount of sacrifice you have to put in to go to that level. It is not just like, you're getting this fame, you are getting to go out there. I mean, if space tourism catches up and like, somebody will fly me up there for a couple $1,000, then I will definitely be the first one to sign up on this list. But currently the amount of sacrifice you have to put on to be on a rocket, to go out there, I think I'm comfortable just chilling out here, just looking at the ocean, just having fun with my friends and family out here. It's because I mean, I can you can do almost similar things that you can do with the satellites out there, because I mean, you can. I'm happy putting a satellite out there if I don't have to do it and somebody else can do it for me.
Fair enough.
It's just, okay, just taking a step back, if you would take all those sacrifices that someone has to make, whether it comes to your family and friends, or whether in terms of your career, or whether in terms of so many health sacrifices and whatnot, if you had to take that out of the equation, I would sign up and I would like definitely want to go there, because I do believe seeing Earth from like that different perspective is just going to change like somebody's life. But going up there does come with all these struggles and all these sacrifices. So yeah, beyond that, I think I'm good in Earth. Earth is definitely amazing.
Because there are a lot of challenges in Nepal, for research. How do you see yourself to be able to contribute to Nepalese scientific community?
Yeah, that is, I think you're talking about like short-term and long-term goals. I think that is definitely my long-term goal. Something I'm guilty of not being able to, so far, not being able to give back to Nepal as much as I want to. But now that I'm in this stage where I've gone through a lot of hardships that, a lot of other students in Nepal would go through as well. So I think there is definitely a potential for me to like go back, and not only in terms of like helping people navigate this scenario that I did, like, growing in a country like Nepal, and then like later on, like I'm now working on doing some cutting edge research in astronomy at NASA. So it is possible, and helping out the community in Nepal is definitely one of my goals that I would like to contribute to once the pandemic calms down a little bit. The other thing I definitely think that can be done is, I think there's a lot of room for collaboration between Nepalese scientists or engineers and what exists out there in terms of like telescopes and whatnot. You don't have to spend millions of dollars to do astronomy research. There are already lots of public data out there that you can use from these satellites already, right? So like giving people this opportunity to know what exists out there and like what they can do from just being in Nepal as well. You don't have to travel abroad to be able to, do astronomy research. And a lot of people, I know at least handful of astronomers in Nepal who have done that from where they are itself. But I think there is a gap between students or young people wanting to do this research, but not knowing what sort of resources exist out there. So hopefully, like, my specific contribution sooner, now that I'm like kind of almost done with my education, is that I can help contribute to bridge this gap between what exists and bringing it to the people who actually want to do these sort of research.
How would you encourage in the career path, let's say?
Sure. I think the first thing I would say is like, sometimes it does feel discouraging that, you don't have everything. Or no, okay, let me take this back. Sometimes it's discouraging that you want to study something, but it's not as readily available in like university level or in like school level around you. But I don't think you should take that as a like discouraging thing. I think there is a lot of things you can do to prepare for your career ahead. If you are really interested in doing astronomy or something related in this field, there is, I have done it, and I'm sure anybody else who's as interested enough can do it too. But, Sanadehi, you have to, there was no like eureka moment for instance. What I'm trying to say is like, Mom, ek din othyanबाट उठेर चाहिँ ल आज म एस्ट्रोफिजिक्स बन्छु भनेर that was never a case, right? It's all gradual, right? सानैमा बच्चा हुँदाखेरि just thinking about my own life, just like यसो आकाशतिर हेर्दाखेरि यो चाहिँ किन यस्तो हुँदो रहेछ, यो तारा भने चाहिँ के रहेछ भन्ने, it was just like more curious के at that point. At that point, I had no idea what being an astrophysicist meant, but that curiosity was there. The other thing was when you like read like even fiction, even when you read fiction, like, or watch things like Star Wars, for instance, like that just like made me more curious. That sounds really interesting. And then like slowly as you go on, you move on to like middle school, high school, you start taking like physics and math classes. So I think another advice I would tell people who want to like join in the field of astronomy later on is definitely don't skip on those physics and math classes. They're definitely important, and they'll definitely help you in a long run. And once you get to university level, you get more hands-on experience. Then you actually get to know what being an astrophysicist means. And if that interests you, then you can keep moving on from there. But even these days, for example, like with the advancement of technologies, like learning more about astronomy or whatever field you are interested in, it's just a Google search away. Of course, you have to, there's a lot of things that you don't want to be doing in Google, but there's definitely a lot of good resources out there. The other thing that I can think of right now is there are so-called citizen science projects where you can actually get hands-on experience on what like professional astronomers do. One thing I remember is there's this thing called like Galaxy Zoo, where you can basically log in and you don't just make a profile or whatnot and try to classify what kind of galaxy this is, like, and doing that at a very young age without any experience. I think that's like amazing. And you can just do it right in front of your computer and you'll get more, you will know whether you want to do that for the rest of your life or not. I think that's what I would say. Yeah, they definitely do not be discouraged that you don't have enough resources around you. There is, there's definitely, it's a very exciting field and there's a lot you can do in this field later for sure.
Thank you for the huge, fundamental background.
Oh, of course.
For a physicist or aspiring anybody to know about like why we need to know physics one yesterday.
For sure. I love what I'm doing, and I think more than that, I think I just love talking about these things, and whenever I get an avenue, I just it's the time. This is the time.
That was Dr. Sumit Dahal speaking about his research in astrophysics. If you have any questions and feedback, please do not hesitate to contact us. We have kept our email address on our podcast description. We hope you enjoyed the podcast, and thank you for listening.
Great.
Awesome. Right. Good luck.
Bye. Thank you, Sumit. Okay.
Bye.
Bye.
Bye.